This is Rocket Science Part 2. We ended Part 1 determining that a guy standing on a skateboard throwing one baseball per second, 100 miles per hour, will have a propulsion force of 6.48 kilogram meters per second squared, which is 6.48 newtons. Newton is defined as a kilogram meter per second squared. Okay, Newton was named after this unit of force was named after Sir Isaac Newton. It's equal to a little less than a fourth of a pound. Okay, we can figure this out because 2.2 pounds is what 1 kilogram weighs at the Earth's surface. A kilogram is a unit of mass, so the force, its weight, is equal to its mass times the acceleration due to gravity, which is 9.8 meters per second squared. Okay, the acceleration due to gravity is 32 feet per second, or 32 feet per second squared. We can also say that the acceleration due to gravity is 9.8 meters per second squared because 32 feet is approximately 9.8 meters. Okay, here's the equation that converts pounds to newtons. We know 2.2 pounds is what 1 kilogram weighs, so 1 kilogram will weigh 9.8 newtons. So if 2.2 pounds equals 9.8 newtons, and 1 pound is 4.45 newtons. And a more accurate number is 4.44822216 newtons, which means a newton is 0.2248089 pounds. So this baseball player who had a propulsion force of 6.48 newtons, we'll multiply that times this number, 0.22 times 0.2248, blah blah blah, all that equals about 1.46 pounds of thrust. Okay, so if instead of throwing baseballs, our pitcher decides to blow dirt out of a straw, he can obtain the same thrust that he had throwing baseballs if the mass flow rate is 145 grams per second. Remember, that's what the mass of a baseball was, 145 grams. And the speed of the dirt's 100 miles per hour. It doesn't matter whether you use baseballs or dirt. If your mass flow rate's 145 grams per second and your increase in speed's 100 miles per hour, you'll have 6.48 newtons of thrust. Here we go. Okay, force equals mass times acceleration, and acceleration is change in velocity divided by a change in time. Looks like our T got wiped out a little bit there. Okay, and if force equals that times that divided by that, we can also say that force equals that divided by that times that. These are three ways of saying the same thing. This equation says force equals mass times acceleration. This equation says force equals mass times the change of velocity divided by the change of time, which is the same as saying that. This equation says force equals the mass flow rate, the mass per unit time, times the change of velocity. They're all three saying the same thing. So how much thrust will a rocket engine develop if it burns 1 pound of fuel per second and the velocity of the burned fuel leaving the exhaust nozzle is 2,450 meters per second? Well, here we have 1 pound is 0.454 kilograms. You may have noticed at the beginning of Part 1 of Rocket Science I wrote on the board 1 pound equals 454 kilograms. It was 0.454 kilograms. Take 1,000 pounds to equal 454 kilograms. Okay, but getting back on subject here, our rocket engine burning 1 pound of fuel per second. Well, we'll use this equation, our mass per unit time, which is 0.454 kilograms per second, and our change of velocity is 2,450 meters per second. So our force is that times that, which is 1,112 kilogram meters per second squared, or 1,112 newtons. And since a pound is 4.45 newtons, we divide this by 4.45 and we get a force of 250 pounds of thrust. The term specific impulse is used to describe how much thrust will be produced by a rocket fuel. The specific impulse of the fuel in our example is 250 seconds. Of course, that doesn't make sense at first because force is supposed to be in pounds or newtons, not seconds. But when you consider the equation, propulsion force equals fuel flow rate in pounds per second times the specific impulse in seconds, you see that force equals pounds per second times seconds, which equals pounds. So if the X-15, that was the first vehicle, that one went into outer space back in the 60s, maybe 50s. Anyway, if it burns 20,000 pounds of fuel in 80 seconds with a specific impulse of 250 seconds, how much thrust is developed? Here we go. Okay, the force is the mass flow rate, 20,000 pounds per 80 seconds, which is 250 pounds per second. And its specific impulse is 250 seconds. So its thrust is 62,500 pounds. The X-15 weighed about 14,000 pounds empty and carried about 20,000 pounds of fuel. Its fuel weighed more than it did. When the X-15 was carried by a B-52 up to 8 miles above sea level and released, its rocket engine would push about twice the vehicle's gross weight. The pilot was subjected to a force of 2 Gs. As the gross weight of the vehicle diminished from 34,000 pounds to 14,000 pounds, the pilot would be subjected to more than 4 Gs. The vehicle would have so much speed at that point that it wouldn't start falling back to Earth until it reached an altitude of 60 to 70 miles above the Earth's surface. As you might have guessed, its stall speed, when released from the B-52, 8 miles above sea level, at 34,000 pounds, was much greater than its stall speed when returning and landing at ground level at 14,000 pounds. But that's the subject of our airfoil section. So feel free to check out Airfoils Part 1 of this aeronautical engineering course if you want to figure all that stuff out. Thank you for your time.